Hello, welcome to this poster. My name is Pierre Kirstetter, and I want to acknowledge my co-authors, Shruti Upadhyaya and Michael Simpson. Progress in precipitation estimation is critical to advancing weather and water budget studies and to predicting natural hazards caused by extreme events, from the local to the global scales. The goal here is to advance precipitation estimation and application by increasing the information content in quantitative precipitation estimation. And we call that probabilistic QPE. Understanding hydrometeorological processes and applications requires more than just one deterministic best estimate to adequately cope with the intermittent, highly skewed distribution that characterizes precipitation. Deterministic precipitation products are subject to conditional biases and uncertainties which are function of precipitation physics, sensor properties, and assumptions and designs in the retrieval algorithms. We consider two examples here, one with ground-based radars and the other with a satellite platform. The multi-radar, multi-sensor system produces precipitation for decision-making and hydrology among numerous applications. And it integrates radar data. The radar observable of precipitation is the reflectivity. The GOES-16 satellite platform provides high-resolution observations of clouds, and in this case, the observable is called the brightness temperature. I will provide more details regarding MRMS, but the application and approach is exactly the same with the satellite. Conventional radar algorithms relate the radar reflectivity to a single precipitation rate, which we know, while we know that in reality a population of precipitation rates can be related to a given reflectivity. So probability distributions of precipitation rates are computed instead of deterministic values to describe the range of possible rates given the radar observations. They quantify more completely the relation between the sensor measurement and the corresponding true precipitation. By including all this information content, we can perform a more documented estimation of the precipitation volume associated with observation conditions. This is the expectation. We can get an improved interpretability of the analysis given by the spread of the distribution. And we can make better decisions with respect to extremes with the tail of the distribution. Precipitation probability maps compare favorably to deterministic QPE. A PQPE scheme is now running in real time in the MRMS research system. We can see how we have conditional biases in the MRMS precipitation estimates as a function of the radar observables and the precipitation types. They are greatly mitigated by PQPE using the same data. We can generate maps of expectations, maps of uncertainties, which indicate the robustness of estimates. The lower the uncertainty, the more robust the precipitation rate estimate is. For example, here in red, uncertainties are higher because of the specific microphysics of convective precipitation. Probabilities of exceeding thresholds are useful for monitoring the occurrence of precipitation extremes that may lead to hydrological hazards. Here, for the satellite, we have the same conditional bias versus the brightness temperature. And in the case of an operational algorithm called Persian CCS, we can see that we have a huge conditional bias as a function of the brightness temperature, and it is mitigated by the PQP expectation. We can derive also the same kind of maps as with the radar. PQP provides the basis for ensembles, precipitation ensembles, that are needed for multi-sensor merging and precipitation assimilation, hydrometeorological hazard mitigation, decision-making, and hydrological modeling. Thank you. for your attention.